Thanks for joining us today. We're going to be discussing a topic called utilizing modeling and simulation to optimize nuclear security system design. My name is Bob Scott. I'm the Vice President of Business Development for AVERT Security Corporation. Joining me today are several gentlemen from the National Nuclear Laboratory in the UK, and they will be presenting some of the information that they have worked on using the tool called AVERT, which is our modeling and simulation tool here at ARES. So they will be taking you through some of those details. What I'd like to do is introduce our first speaker. Robert Roger, who is the business manager for Nuclear Security Safeguards and Nonproliferation at NNL. Robert's been recently appointed business manager for the National Nuclear Laboratory for the Nuclear Security Safeguards Nonproliferation portfolio. Having over 10 years of experience in the nuclear industry from working for the Civil Nuclear Security Regulator as a senior site inspector and the lead assessor for security aspects of the generic design assessment of the EDF and AREVA UK EPR and the Westinghouse AP1000 reactor designs. Previously, Robert spent over 20 years working for the UK Government Home Office as a program and project manager researching, developing, and evaluating detection systems for critical national infrastructure sites and prisons. So Robert, over to you.
Thank you very much, Bob. For those that don't know who the NNL are, I'll give you a brief description. The National Nuclear Laboratory is a company owned by the UK government and managed under contract by the SBM Consortium. That's Serco, Battelle, and the University of Manchester. NNL operates as a commercial business and receives no direct grant funding from government. We play a key role in the UK and global nuclear industry. With over 10,000 person-years of nuclear industry experience across the whole fuel cycle, our core business is to provide the experts and technologies to ensure the UK nuclear industry operates safely, securely, environmentally responsibly, and cost-effectively, today and for the future. We have around 800 staff, with more than 400 of those being scientists and engineers. In addition to our products and technical services across a whole range of nuclear industry sectors, we have an innovation program with 5 signature research areas that have been identified as being central to the National Nuclear Laboratory mission. One of those research areas is the nuclear security and CBRN area. As business manager for security and safeguards at the National Nuclear Laboratory, we at the laboratory have taken a professional interest in the use of modeling and simulation techniques for developing solutions and optimizing performance in the nuclear industry. Within my business area, the security team have looked at the use of modeling and simulation methodologies to optimize nuclear security system design. They identified an internal customer who will describe their needs next. We will then present a case study of the work we carried out, concentrating on the construction of the model, the simulation of attack scenarios for theft and sabotage, the lessons we learn, and our views on the strengths and weaknesses of this approach to security system optimization. In the United Kingdom, we talk about the NIMCA, the Nuclear Industry's Malicious Capabilities Planning Assumptions. That's our equivalent to the Design Basis Threat, the DBT, used internationally elsewhere. That document articulates the threats, their motivations, intentions, and capabilities of potential adversaries against which protection systems are designed and evaluated. From the laboratory perspective, it's important we analyze the strengths, weaknesses, opportunities, and threats to using these technologies and determine whether the approach meets the scope, cost, and schedule of security works, and most importantly, the quality of the information that a customer requires to meet their needs. I shall now hand back over to Bob, who will introduce our next speaker.
Thank you, Robert. So next on our agenda is Mr. Jeremy Davison, who is Head of Security for NNL. In this position, he is responsible for ensuring that NNL meets the regulatory requirements for the protection of nuclear material other radioactive materials, and sensitive nuclear information. He also has the responsibility for the protection of NNL's other assets from a commercial perspective. Personnel security for the NNL, including clearance, vetting, and pass processes, is another important area of Jeremy's responsibility. While carrying out this role, he has regular and close interactions with a variety of stakeholders, including government, the civil nuclear industry, the police, and the supply chain. So, Jeremy, welcome.
Thanks, Bob. This morning I'd like to tell you about how we in NNL piloted the use of AVERT in the UK. To put this into context, we in the NNL have a sensitive, high-security facility that's currently being commissioned after a period of inactivity of a number of years. And to put this into context, it's worth saying that this is a multi-purpose, complex building containing offices, inactive laboratories, highly active laboratories, and plutonium laboratories in a facility made up of a number of floors. So during this period of inactivity, the national security standards in the UK had changed. The risk appetite of government had changed, and therefore some security enhancements were required. Over the same period, the regulatory framework had changed from one that was mainly prescriptive to one that was now outcome-focused. And as such, not only did we have to carry out the enhancements, but justify that that enhancement work met the appropriate standards. So what did I do? Well, we decided that as a national nuclear lab, it would be a good opportunity to trial the use of the AVERT vulnerability modeling tool to help demonstrate how we meet the requirements. So we went about generating a business case based on cost savings and on the longer-term use of the model, because once it was already made, it could be used for temporary security arrangements or other modifications made to the facility. To enable the model to be used, we needed to gain understanding from the regulator and some other stakeholders that it was appropriate and that the answers it produced would meet their criteria. So we went about that. We modelled the whole facility, including the surrounding area and the local site perimeter, to enable realistic scenarios to be modelled. And once the model was physically created, we then detailed it with all the appropriate security features, such as the delay times of the doors, the fences, cameras, etc. And then we looked at the scenarios, and as Robert's mentioned there, we based these on national standards that were the UK design basis threat, known to us as the malicious capability planning assumptions. So this detailed actually what sort of threats we were going to put against the building by the model. So in terms of the output of the pilot, we run various scenarios as planned, and that was where things got interesting from my perspective, because it allowed me then to look at the results and to see what had happened. And of course, when you see that, then you start going back and wanting to make some modifications to the physical protection layers. And on a model, you can do that by just making some modifications. So we ran a number of what-ifs just to tweak the model. The reports from the pilot indicated how the enhancements proposed had met the majority of the requirements, but not necessarily all of them in all cases. What the model did produce was quantitative evidence as to the predicted level of success, and in some cases that meant that in some scenarios there were some failures. But it did allow us to identify those and look at which areas needed further attention. And one of the best things for me is that having done the pilot, the model is there now available for further use and ongoing use, so I have a facility that's fully modelled, has the security features, and we can use it to do further work on. So with that overview, I'll hand you back to Bob.
Thank you very much, Jeremy. Before I proceed on to introducing our next speaker, I would like to remind everyone that you have the ability to type in questions, which we will work to answer at the end of this presentation. So next is Mr. Norman Bird, who's the Senior Technical Lead Manager for Nuclear Security. He's been doing nuclear security at the lab. He has over 32 years experience in design, development, construction, and protection of major nuclear sites and other infrastructure projects, including the Thames barriers, Sellafield site infrastructure development, early geological disposal facility conceptual work, nuclear site enclosure, etc. Recently, he has been the lead on the NNL team on-site facility security vulnerability assessment using CAD, GIS, imagery, and 3D modeling and simulation techniques. Prior to joining NNL, Norman was the Group Assurance Manager for Security, Safeguards, and International Affairs for BNFL. Norman is a qualified civil engineer and holds a Master's of Science in Qualified in Geographic Information Systems. So with that, Norman, I'd like to have you begin.
Thank you, Bob. Good morning, everybody. The following presentation will explain our approach, early work, results, benefits, conclusions, and what we perceive as the next steps. As you can appreciate, we have limited time available today, so I will be quite brief in my overview. As a general subject area, modelling and simulation isn't new. It's been around for many years. It's often confused with computer-aided drawing and design. It's also been extensively used in the civil nuclear sector to date, e.g. in nuclear security, nuclear safety compliance. This could be looking at reactor performance, seismic performance, or even environmental performance from a regulatory or design compliance perspective. Nuclear security modelling and simulation is therefore an emerging subject area. Historically, there are various other approaches around, from spreadsheet up to dedicated programs for undertaking vulnerability assessment work. The uniqueness of this new approach is that it combines high-end 3D visualization with substantial data libraries and a powerful simulation capability. This gives the user a considerably better graphical user interface in order to prepare and demonstrate how assets and facilities are protected and how well this will withstand a combat or attack scenario. When NNL was first involved with this approach, it is well worth noting that at this stage, this approach was already a mature solution. It had already been tried and tested in the US for over 10 years on various sites and has or is likely to receive US accreditation certification from the following bodies: the US Departments of Homeland Security, Defense, and Energy. This underlines the maturity, capability, and confidence the US have in this modelling and simulation approach. It clearly demonstrates that departmental or regulatory bodies can achieve a level of confidence in this approach and use it as another vulnerability assessment alternative to formal state compliance. So why did NNL undertake the work on pioneering this new approach? Well, basically NNL could see there was great potential in developing something like this and had been considering developing something similar itself. It was only when the approach was identified that the real benefits of integration as an early adopter was apparent. It is the commentator's belief that if the approach had been available in the UK 10 years ago, this would now be in mainstream use across the UK nuclear industry. This kind of capability for computer-based modelling and simulation for security vulnerability assessments is now long overdue in the security sector compared to nuclear safety. In addition, we had to trial run this approach against a UK nuclear facility to see how the relationship with UK regulation, our definition of protective measures, and the postulated design basis threat were embedded in the approach and then simulated to see if we could generate meaningful output that could add value to the process. From a compliance perspective, duty holders or licensees have been required to produce some form of vulnerability assessment to satisfy nuclear regulators that physical security is commensurate with the postulated national threat. Historically, this vulnerability assessment approach could alternatively be based on a variety of different techniques, from spreadsheets to coded computer programs. The new approach used by NNL gives a slightly different take on vulnerability assessments. In brief, it takes a red or adversary team and a blue or defence team, plus an accurate three-dimensional model of the site or infrastructure or other asset, be it a ship or a harbour, etc., plus physical protection, accurate performance data for all aspects of protective measures, plus conditions, terrain, etc., and runs a simulated attack, numerically identifying how effective the postulated security measures actually are. NNL have found the approach used to date has given robust and realistic output, and the approach has helped to air weaknesses more effectively and has served as a core model for understanding and debating the security design adopted. By moving towards auditable models in future, that best emulate actual physical security regimes, they are fundamentally more likely to identify inherent vulnerability than occasional visits by site inspectors or staff. The approach is also capable of systematically reducing subjectivity from experts so that opinions are consolidated, fully embedded, and results borne out in further facility simulation. This collaboration by all specialists involved around the core or centric live model, rather than all sharing different opinions, is very important. The simulated results derived means that results are going to be more consistent, more reliable, more highly valued, and more critical to state compliance and successful ongoing business in future. So why is the development so important for the nuclear industry? The industry has a constant desire, regardless of state-owned or private operation, to achieve steady-state operations, i.e. no incidents or no surprises. Approaches like the one described in this webinar can help to better mitigate serious incidents by giving improved compliance, resilience, and secure and consequentially safe operation. Although serious incidents are rare, when an incident does occur, the ramifications are felt by the whole international nuclear industry. The industry is also facing more pressure to be commercially effective, as traditional state-owned operations are gradually becoming more contractorized. Executive boards of these contracting organizations are demanding more and more reliable information to demonstrate expenditure and investment decisions, and are rightly asking key questions of security provision. So this approach is capable of doing financial what-if scenarios as well, but the financial side was not something NNL tested in our early adopter work. So why is it important to NNL? NNL operate in a dual role arrangement. We are a facility operator facing national nuclear security compliance, and we also fulfill a national R&D capability. NNL is a facility operator and is required to achieve ongoing compliance and good operational availability. As an organisation, we don't want uncertainty or vulnerability, and hence cost variance in our asset base or operations. We also need to maintain full compliance and the ability to earn income from our facilities. So operationally, we, like the industry itself, also desire steady state conditions to fulfill our business objectives. So what were the aims of the study itself? The NNL study work was really focused on seeing how well the approach actually dealt with a licensed nuclear island, which is typically complex, varies in structural integrity, and is not usually symmetrical in layout. The key NNL aims can therefore be summarised as trialling the approach on a complex UK nuclear facility, evaluate its identified, document our findings for UK and international benefit, fulfil the UK early adopter role in this area, and utilise our reach back to the US for technical software support and training. So what were the key components of the study? To quickly summarise, the key components of the study were to undertake model construction and simulation for chosen threat scenarios and report, to confirm the new approach had value over traditional techniques for NNL as the operator, the UK nuclear industry, and the UK itself. To ensure the work was aligned with dates, preparation of a vulnerability assessment for the security options and specific facility commissioning plans. And also, now I will explain over the next few slides the process that we actually followed. The process starts with the data phase, which in my personal opinion, after completing this project, I believe is fundamentally the most important phase. Get it wrong here and the whole approach is likely to be inadequate to meet the needs. The best information available to achieve the desired fidelity of the model needs to be sourced and verified at this point. So the model and its actual fidelity is a technical judgment call. Too detailed and the model takes longer to run. Inadequate in detail and the quality of results will not be achieved. The next phase is the modelling phase, where the information sourced in the previous phase is brought together and converted into a representative and capable base model with a suitable fidelity to undertake the planned assessment. At this stage, the libraries will also be populated with the best available information. This may be nationally quality assured information or it may not. In our work, it was actually a mixture of the two. This again is a technical or professional judgment call. At this stage, we would also introduce details of the adversary, defending force, and other fundamental criteria like assumptions, conditions, etc., so that the model is now ready and capable to accept a defined threat scenario from the design basis threat, undertake simulation, and produce reasonable results. The next phase is the simulation phase. In this phase, each of the threat scenarios are introduced so that full simulation of the model and its criteria can be undertaken. The simulation will demonstrate pathways taken, significance events occurring, effective neutralization, and concluding overall system or security effectiveness. In this simulation phase, preferred paths can be set, or alternatively the model can be given locations of adversaries, guard force, targets, and end conclusion points, so that the model can evaluate all the different nodes and derive its own preferential pathways based on criteria set, e.g., for example, fastest path or least detection, or a mixture of the two. The next phase is the output phase, and this includes the review of the simulation phase and its outcomes. It also involves consolidating results into meaningful reports as required from the vulnerability assessment exercise. I will talk about results in more detail later in this webinar. The final phase is the verification phase, which was not undertaken as part of the NNL work to date, but represents full calibration of the assumptions, criteria, and the model itself. A model represents the real world. In order to verify its accuracy and results reliability, it should be at least periodically verified with a performance test or live exercise in the field to ensure model criteria are as closely representative of real-world activities. Without the verification phase being undertaken, the modeling and simulation results can be openly challenged, so data needs to be accurate and physically verified in the field to underpin the inherent overall data quality of the vulnerability assessment. So to summarise, the four phases of the work undertaken by the NNL that I have just explained were Phase 1, the data phase, Phase 2, the modelling phase, Phase 3, the simulation phase, Phase 4, the output phase, and finally the one that NNL have yet to formally do is Phase 5, the verification phase. So what might a finished model actually look like? Here is what a potential facility might look like following the vulnerability assessment approach. This particular model has been rendered to make it look more realistic in appearance. NNL's priorities were not about making the model look visually realistic at this stage, as this did not impact on the overall analysis or improve security. At this point, it is worth briefly mentioning data libraries as well, and the impact these may have on the model outcome and hence quality of the overall process. Alongside the graphical 3D model itself, the data libraries and their attribution to the model are an essential component of the overall approach. The core criteria that need to be met in establishing the data requirements for libraries, these are: first, data should be accurate, or as a line manager of mine used to say, garbage in, garbage out. So it's essential that you start on the right foot. The second point, data should be based on performance-related outcomes. Third point, data should be representative of the facility. And fourth point, data should be from reliable sources. So what were the early benefits identified? I will now describe to listeners some of the early benefits identified by NNL during the work. These can be summarized again as follows. Accurate model information. Moving on, Bob. Accurate model information. Early accuracy in the model creation pays dividends through the rest of the process. Early review mechanisms and operational feedback. Think about the process, appropriate checks, balances, by whom, when, and what are your success criteria. Site visits and model visits. Site visits are paramount in ensuring errors or misunderstandings don't accidentally creep into the model or assessment, and any that do are readily addressed and removed. There's also model simplification, if there's any areas that you can reduce the complexity of the model to take it, and also access to timely support and subject matter expertise. Alongside the benefits, we also experienced a number of challenges or findings. Challenges at this stage could be summarised into errors associated with converging data and importing data into models. Our early experience suggests we believe we can develop ways to overcome this by developing internal best practices going forward. My advice to anybody contemplating this kind of approach is to take time to assess the data sources and try and undertake some trial data integration to see where any quality issues may originate from, what they are, how extensive they are, and how you may mitigate them. Designing data issues out very early in the process is ultimately the way to go. As you can see from the illustration in front of you, results can be delivered or published in various ways. There are many ways of exporting and illustrating the desired results. It is really down to individual organisations, regulators, etc., to analyse the approach and decide how to best answer the key killer questions for defining security performance. So reporting of results from this approach is very flexible and dependent on your own expectations from the approach. It is also dependent on your anticipated audience, and so could be operational, tactical-based, cost-based, or compliance-based, just to name a few variants. I will now review the results approach taken by the NNL. Our aim in this work was to be able to give the regulator clear, meaningful, comparable information about how the facility performed in different threat scenarios. This modelling and simulation-based information being directly capable of underpinning UK nuclear security compliance. The diagram shows our approach, and I will discuss this in more detail shortly. As mentioned earlier, the approach supports the production of performance information. In the absence of any UK national modelling and simulation performance thresholds for security effectiveness being set, it is the individual operator's responsibility to look at internal requirements, state regulations, and decide what is actually required to demonstrate actual effectiveness. NNL's approach focused on delivering system or security effectiveness against what could be deemed as a peer set of compliance or expectation criteria. Following enquiries with US colleagues, we decided to adopt a numeric graded or threshold approach that could in future be used by UK operators using modelling and simulation as a prototype for national security compliance criteria. It is worth noting here that the NNL approach also then moved into a more detailed approach underpinning these results, which we have called the sensitivity analysis phase. This is essentially the fine adjustment of the measures versus the security effectiveness percentage. I will now spend a few minutes looking at the overall results reporting stage in a bit more detail. So the real killer question for everybody here is, what percentage of security effectiveness is deemed acceptable? In reality, this question could actually be reformed and asked twice. What does an operator deem as acceptable, and what does a regulator or state deem as acceptable? I say this because the drivers for business are in essence quite different from the regulatory or state drivers. Businesses or operators are more likely to be risk averse in their approach and more likely to be interested in cost optimization versus percentage security effectiveness improvement, whereas a regulator or state is likely to be aiming more attention on a generally high level of security performance being achieved and demonstrated in practice. The slide presented illustrates this streamlined approach taken, with the individual threat scenarios listed individually on the x-axis, A, B, C, etc. at the bottom of the slide. Individual security effectiveness percentage values derived straight from the approach on the y-axis. On the left there, And on the right-hand side of the diagram, the actual performance thresholds assumed for those percentage security of effectiveness zones. So you can see unacceptable, improvement needed, good and excellent. As I have experienced in my previous work as a nuclear security assurance manager, a simple approach means most time is then focused on delivering security performance improvement and increasing security readiness rather than debating the actual criteria set. It can be applied to either state-run or contract-secured facilities without change, and in particular this is an ideal approach for states where nuclear security has been contractorized, both US and UK being typical, giving private companies very clear and unambiguous national performance expectations for nuclear security that need to be fully met, which could be fully included as a contractual item in addition to a compliance obligation. So looking back at our approach from a point of direct challenge, what are the benefits we identified? I'm not going to review all the points noted on this slide in detail. I have chosen 3 top benefits I see as the main advantages. And these 3 are, basically, the approach gives a rapid 3D assessment of complex facilities. It clearly demonstrates compliance and operational advantages, and it provides fundamentally better engineering appreciation and accurate combat simulation. The main benefit identified is that from a UK perspective, given we have now introduced outcome-based regulation in 2012, we now have a credible modelling and simulation approach that can take this national expectation through to a measurable outcome conclusion that can be demonstrated and supplied by each operator via modelling and simulation. This gives operators the detailed tools and techniques to undertake a cradle-to-grave approach for each of these threat-based outcomes, ultimately clearly demonstrating to interested parties, be that the regulators, state, etc., where security is adequate and where there is room for improvement. There is scope for commercial linkage as well, e.g. links to funding programs and also site targets, etc. So to summarise the conclusions, the approach demonstrated gives the operator the ability to be able to better manage, comply and develop demonstrable performance, mitigate the threat and manage the overall security cost planning. The approach also brings together all relevant information in considerably more detail and a core auditable model being available in order to better understand and articulate the best and most economical security solutions. Many secured sites undertake frequent performance testing like live or tabletop exercises to challenge the security measures in place. There are 2 clear benefits in this area. As noted earlier, the exercise results can be used as the verification phase for the model, i.e. model results are tentative until exercised and verified in the field. The model itself can also now become part of the desktop exercise itself, quickly being changed to suit scenarios or postulated threats, also showing tactical responses and learning from the outcomes. If necessary, scenarios can be taken from the model and acted out in an exercise to compare desk results and field outcomes together. Both the above points must culminate in cheaper, more effective and demonstrable evidence of high-quality security provision that is also auditable. The perceived organisations that can benefit are state departments as asset owners and those responsible for critical asset protection, e.g. critical national infrastructure, etc. Nuclear site duty holders, facility owners and site operators, regulators and other security practitioners, e.g. guard force, transporters, etc. At this early stage, the approach did not save money for NNL. It is our belief that in time the approach will become considerably more thorough and effective and at least as cost-effective as traditional techniques. It also gives a coordinated platform to explore, exploit and challenge the current cost model and the compliance expectations so that a tighter, more engineered demonstration of computer-based evidence is possible. We believe there is real value in this approach to manage and refine the regulatory requirements, manage the operational aspects to meet that requirement, and foster the ability to make clearer business decisions around the cost versus effectiveness debate in future. So in this webinar we have briefly explained the approach, its results and benefits, etc. NNL intends to continue to use the approach productively to underpin all its security compliance and operational requirements for all our facilities. In a wider national laboratory early adopter role, we continue to demonstrate the benefits of this approach to the wider national community where this may have a future benefit or impact. Most particularly, this is across the UK nuclear and critical infrastructure national asset base, but could include any asset infrastructure in future where some form of operational, regulatory or cost oversight is required going forward. The NNL will shortly be publishing an overview paper on the work to date, and this will be available from RS Security or NNL. Closing summary, I hope that in the short time available, this webinar has at least given you a chance to appreciate the potential of this emerging technology, which could really impact on the future of nuclear and other critical infrastructure security, and the responsibilities of staff required to protect and assess these facilities on a day-to-day basis. This new approach will help practitioners to be more comprehensive in their assessment approaches, which must lead in the end to improve security performance and ultimately gives us all an additional ability in our work to help us to maintain a more thorough, consistent and higher state of vigilance in the protection of nuclear and other critical assets, infrastructure and operations. If you need to ask any further questions or advice about this webinar, please don't hesitate to contact me via my email address, and this will be available via the webinar interface. Thank you for listening to this webinar. Thank you, Bob.
Okay, thank you, Norman. So what I'd like to do now is wrap up in a few additional items to talk about. One is to let you know a little bit about ARES, and then talk about the optimizing part of this and some of the areas that we're working towards, and then talk a little bit about some future developments that we're currently engaged in. Norman had mentioned early on in the discussion about the maturity of the product. ARES as a company has got over 20 years of work in the risk management field. We've done a lot of work around DoD, NASA, and a lot of the talents and techniques that we had developed over that time went to building what is now the AVERT product. One of the things that we were required to do as we worked with our federal government folks is to go through a validation, verification, and accreditation process. So we are now currently accredited by the DoD, soon to be by the Department of Energy. We've also gone through an extensive certification process with the Department of Homeland Security, which really is to validate that security of this type has liability indemnification. Another area is that we have done some work and helped build some best practice guides for the World Institute of Nuclear Security. So all of these things over the years have been items that we have gone through to really validate and verify that the modeling techniques and approaches that we've taken meet close to real-world conditions. And as you saw from what Norman was talking about, they actually proved that out in their site as well. From an optimization side, Norman talked some about the cost advantages, and not an area that they focused on predominantly for the early adopter role, but an area that we've spent a lot of time working on is being able to make sure that we can take a much larger run of activities and scenarios so that we get both a high degree of confidence that we've adequately looked at a lot of different capabilities, a lot of different measures, and also to take a look at the results of those. So we did a test just recently and laid out 12 threat configurations, 180 defense configurations, and basically within the modeling environment we can set those all as optional, then let the process run and look at all the various combinations of these. So that yielded around a little over 2,000 scenarios. And then against that we ran multiple attacks, and so we ended up with close to 1 million attacks that we did using our enterprise version that was allowed to run across multiple processing systems, so 12 cores on 3 computers. So basically reducing about 34 days of compute time down to 3 days of actual runtime. So running these models, just to kind of reiterate some of the things that we had with Norman's discussion, is the model allows you to either generate pathways. Which way does the adversary take to reach an intended target, and then simulate the attacks and then the response to those attacks. So basically 1 million of those were generated. What we did is we took all that data and we put it into a spreadsheet and associated it with some likelihood and cost data. So very quickly it was easy to kind of go down through and look at various configurations against various threats and look at the probability of effectiveness against the cost to do that. So back to some of the early discussions that Norman led us through, that's really the net of what this product does for us. So this was a visual way to really start to look at, green is good, I had high, effectiveness, but was it within a budget that was appropriate or applicable for my environment or my site? With 1 million rows and 1 million, sets of data and attacks, that gets to be a little bit cumbersome. So one of the things we've been looking at is how do we make that more effective, and I'll talk about that in a moment. But first, one of the challenges that Norman brought up was the modeling. So because AVERT basically allows you to use 3D data, originally and in our current product set, we have what amounts to a 2.5D model. It does use design data from a CAD package. It does use geospatial data. We do go in and create the nodes that we assign performance data, terrains, etc. And on the left-hand side of the slide that you're looking at now, you can kind of see an example of that. So you see that it is highly generalized, that things are square and blocky. Things are brought in layers to build up floors and terrain. And while that is effective, it does take a bit more time and a bit more training on the early sides of site characterization. So because NNL is a collaboration partner with ARES, we've taken a lot of their feedback and input, and our next release of product in September will use an open format. So we're moving away from our proprietary format to a format that allows us to directly ingest CAD data, GIS data, and retain a lot of that 3D geometry. So you'll notice the same representation of the left side now in the new 3D geometry on the right side. Looks a lot more realistic. It greatly shortens the time to capture the physical characteristics of the actual site that you're modeling. What we have done now is we have a nav mesh generation process that goes against that particular model to generate all the nodes that are used to do the pathway analysis. So one of the areas that we've learned in working with NNL is some better techniques to get that front-end model so that we can begin characterizing the site with the adversaries, the guard force, and the technologies that we want to utilize. So what we've done is we're taking a look at our current capabilities and are beginning to evaluate, and we've done some early prototypes on how do we get a much better simulation result to do optimization. So one of the areas we're doing is we're taking a look, and this screen depicts kind of areas where we already have the technology ready to go. It's in our existing product. The yellow boxes and the yellow areas are kind of medium, so we're still in development and research, and the reds are sort of the future and the areas that we've got to spend a lot more time on the research side before we go to develop. So we can do the 3D modeling. We have very extensive performance data library, 50,000 elements to date, with a library editor to allow customers to work on enhancing, expanding, and extending that library. We have the simulation engine. We are moving to this new modeling format. But some of the areas that we're going to start looking at and have kind of some of the early prototypes done is, taking a look at a better system designer, so a bit easier way for a security practitioner to go in and set up the model, to set up your target sets, look at your adversary forces, etc. Another area is moving from the kind of the terrorist threat to a different or an expanded threat matrix. The high consequence, low probability events like what happened at Fukushima. So being able to model and look at natural and man-made events that are not just a terrorist attack, but could be weather conditions, tornadoes, tsunamis, you name it, or just accidental things that cause interruption to a site security or a site operation. The optimization engine then allows us to more rapidly run those multiple scenarios, getting into in excess of millions to millions, and putting all that information into a data store so that we have quick access to it. Moving over to the right-hand side of the slide is looking at these various tools. We today have a scenario playback, but we are looking at enhancing the report capability. As you saw from Norm's slides, there are an extensive numbers of reports that you can get out today, but we continually look to enhance and create different reports and maybe more intuitive reports for a lot of the security practitioners. Getting into training exercise simulators where we can actually start to exercise and train people through the simulation environment. Perhaps being able to use it to allow for, say, the site to look at and evaluate the use of fire engines for providing emergency coolant, during an event like a Fukushima or a tornado or what have you. Being able then to get into some risk displays in a real-time system. So we're spending a lot of time looking at, could we use a display of a set of these outcomes? So for instance, on a given day or shift, I know what my current threat posture is. I know what my guard force complement is. I know what all my technology is and how it may be working or maybe offline due to maintenance. And I can basically go into the system and pull out that result set that would give me a condition or a kind of a posture of how my site is set up for those conditions at the time. And being able to very quickly, and we're talking minutes and hours, of being able to go in and through a parametric kind of interface to say, now I've got a camera offline on the north perimeter, what does that do to my overall system effectiveness or my current vulnerability? So those are the areas that we're moving towards to take this modeling and simulation and move it from a pure vulnerability assessment tool on into an optimization tool and moving on into more kind of risk management, risk displays, site capability displays. Another area that we're spending some time on is in the training and visualization. We do have some capability today with one of our tools, but we're taking some deep looks at some of the third-party tools that are out in the industry and being utilized today, by defense forces and whatnot. One of those tools we're looking at from Bohemia Labs is the VBS2 or Virtual Battle Space Simulator. One of the things we've prototyped is being able to take one of the results out of that million attack scenarios that I described earlier and being able to ingest and replay it through the VBS2 interface, where I have much more realistic and much more capable ways of showing what an attack would look like as it unplayed. So being able to go in and show a particular DBT with a set of capabilities, actually watching the 3D model in a kind of a playback scenario. Then use that same tool as a training platform that we could go in first role, first player role kind of interaction with that environment. So we are doing some work in that area. The visualization becomes very key in order to have security officers, security folks being able to communicate both the risk and the cost and the result of not doing one or the other or doing something to some level such that I can actually see that scenario play back. And more importantly, because we've solved all those different runs, being able to, when the regulator says, yeah, I get that, but what if this condition? Well, being able to go in very rapidly and replay that condition within minutes to hours rather than having to go off for 2 months and rerun something would greatly enhance, we believe, the capability of the overall system.